Hello again, it's Kenny with Matrix Linear Algebra. If you're here for solving a linear system, then go to the time in the description. For now, I'm going to just go ahead and show you the book that I'm going to be using. Now, the book that I'm going to be using is called Linear Algebra 3rd Edition. It's Applications by David C. Lay. I'm not sure which math book you're going to be using, but that's the one that I use throughout my course, and the one that I'm going to be using now. So I'm going to be covering 1.1 in this video. I hope this video doesn't drag out too long. I'm going to cover an introduction to linear equations / systems of linear equations, the matrix notation, and solving those linear systems / matrices. Now, based on my experience, the vocabulary terms that seem to be kind of interesting, that kind of useful actually, are solutions of a system, consistency or inconsistency, the size or M by N matrix, the elementary row operations, whether or not a solution is unique, and the two fundamental questions about linear systems, which are consistency and uniqueness. I will define the vocabulary as I go on. Now let's begin. 1.1, you're probably already familiar with y equals mx plus b as a linear equation, or just y equals mx. Something else that might look like a linear equation would be z equals a sub 1 x plus a sub 2 y. And a more generalized form of that is a sub 1 x sub 1 plus sub 2 x sub 2 plus dot dot dot, which means it keeps on going, plus a sub n times ax sub n equals b. And in 1.4, I believe, is when you get introduced to the matrix equation ax equals b. But I'm not going to cover that right now. That's for later on. Now, if you have no idea what I'm talking about, well, pretty much an equation that I'm going to use that looks like this is actually 3x sub 1 minus 5x sub 2 equals negative 2. That's all we're talking about. It's not very foreign, it's not too complicated, and it's just the beginning of the book. It's where we start off at. Now, then the book decides to tell you what are linear equations. I mean, not linear equations, a system of linear equations, I'm sorry. And so a system of linear equations is basically something like this, and then added onto the bottom 3x sub 1 plus 4x sub 2 equals 2. That's it. Just two linear equations, one on top, one at the bottom, or more linear equations. You could add as many linear equations as you want, and that would become a system of linear equations. Now, for a little bit of vocabulary with these things, a solution of a system is a list of numbers denoted s sub 1, s sub 2, dot dot dot, all the way to s sub n, which could be substituted for x sub 1, x sub 2, all the way to x sub n, which makes the statement true. If you're not following, that's alright. I had to think about it for 2 seconds. It's just any number that could go into these x's that would make this true. These x's, this true. It's at this point where you could start thinking of the solution of these linear equations for what they are. I'm sorry, not the solution. These linear equations for what they are, which are lines. Now, these lines could come in a few flavors. Sometimes you might have a line that's parallel, and so there's no solution. So there's no x's value that could go into these x's or in a system equation for these two lines. There's no solution. There is where you would see one line with multiple equations for that one line, and you will see an infinitely many solutions because the lines are overlapped. And then you could see two lines intersecting at one or more points where you would get one or many solutions. Usually it's only one solution that we're talking about, I believe. Anyway, now on to the matrix notation. Now, we remember, we just went over the linear system, which I could write right here, the one that I've noted down, x sub 1, 2, x sub 2 plus x sub 3 equals 0, 0 plus 2x sub 2 minus 8x sub 3 equals 8, then negative 4x sub 1 plus 5x sub 2 plus 9x sub 3 equals negative 9. Now that would be our linear system. So the book just very nicely just tells you, well, take all the coefficients and write them out as, for x sub 1, that would be 1. I mean, for row 1, I'm sorry, for the first equation, row 1, that would be at 1, negative 2, 1, 0, 2, negative 8, negative 4, 5, 9. All right? So that would be our coefficient matrix. And you might see that I actually left out these guys. I'm getting to that. I could write them at the side, but I'm going to choose to rewrite the matrix. 1, negative 2, 1, 0, 2, negative 8, negative 4, 5, 9, and 0, 8, negative 9. That would be the augmented matrix. That's what it's called. All right. So to actually make this look nicer, because we might not know what we're talking about, a coefficient or an augmented matrix, what I tend to do is just add a dotted line right between what would be the coefficient matrix and what's on the right side of the equal sign, the constant, the one that doesn't have a variable next to it. It's at this time where I would like to talk about the size, actually. You could tell that this is a 3 by 4 matrix. That is 3 rows by 4 columns, which the book tends to denote M by N. You got to remember this because for the rest of the book, we're going to be referring to rows by columns as M by N. And that's going to be showing up in an equation later on. Now we're going to move on to solving a linear system. What I mean by solving a linear system is finding the values of x sub 1, x sub 2, all the way to x sub n, that when plugged in makes the linear system true. What this means for a matrix when solving a linear system is that each column has a 1 in it, and that the matrix has a triangle of 3 zeros at the bottom left corner of the matrix. Let me show you what that looks like. That would be 1, 0, 0, 1, 0, 1, and then all of this is something. All right, you could have a 2 by 2 matrix where it would look like this. I'm sorry, can you see that? Where it would look like this. 1, this might be something, and then 0, 1. There would be only 1 in this in the bottom left hand corner. Let's see, where am I? So now we're going to cover elementary row operations. They are taking a row and multiplying it by a number and then adding it to another number, interchanging the two rows, and scaling or multiplying a row by a non-zero constant, otherwise known as a scalar, which will be covered later on in the book. If you don't know what I mean, you could always rewatch the video at that point. If you tend to grasp things better when you're listening. But for now, I'm just going to jump into covering an exercise with you. I mean, an example. Now, the example in the book would be this that I'm going to write out really quickly. It's probably not the same one that I just wrote out, but I'm going to use this equation twice. And there we are. Now we could go through the exercise of writing it as a matrix. Okay, and now we could perform row operations. So for here, I'm going to write down, let's see, what did I do? What I'm going to do is I'm going to take row 3 and add it to 4 times row 1. I'm not sure if you could see that. All right, so I'll actually write it out now. 1, negative 2, 1, 0, 0, 2, negative 8, 8, and then negative 4. So 1 times 4 is 4. Negative 2 times 4 is, 2 plus negative 2 times 4 equals negative 8. Then you take, why did I write 2? That should be a 5. And then 9 plus 4 times 1, that is 4. And we finally take negative 9 plus 0 times 4, that equals 0. That is equal to 1, negative 2, 1, 0, 0, 2, negative 8, 8, 0, 5, 6, 7, 8. No, wait, that's not right. Let's see. Yeah, that should be negative 3. Okay. Just making sure that my math is right. This is 13, and this is negative 9. Again, with my dashes, my crooked dashes. Now what I'm going to do is take row 2 and multiply it by half. So that should look like 1, negative 2, 1, 0, 0, 1, negative 4, 4, and 0, negative 3, 13, negative 9. And finally, I'm going to do something that I did like over here with the first one. That would be row 3 minus 3 times row 2, and that is equal to I should really be using arrows. Anyway, that is 1, -2, 1, 0, because nothing changes there. Nothing changes at the second row. 0, 0, and then that is 13 minus 3. Yeah, 13 minus... No, 13 minus 12. I'm sorry, there shouldn't be a minus, there should be a plus. 13 plus -12. That would be 1. And then -9 plus 4 times 3, so -9 plus 12. That would be 3, I believe. Yeah, that's 3. Oof, I feel a little confident. Don't worry. With some practice that your teacher probably gives you and the problems in the book, with repetition, eventually you'll be able to do this mentally, which is what I did with this one, and what I did with this one. These two are actually examples of taking a row, multiplying it by a number, and then adding it to another row. See what I did? I took, this one looks clearer. This is row 2, multiplying it by a number, and then adding it to another row, keeping the row that I multiplied by a number, by a scalar, the same. See that these two are the same. The only one that I didn't do here would be the two that I didn't, the two row operations that I didn't do here are interchanging two rows and multiplying. No, I did multiply by a number. I took row 2 and I multiplied it by half, or I just divided by 2. Same thing. Okay. I know this was probably sloppy by a professional's terms, but I'm not a professional, and I have a script that I'm reading from here that is telling me that I'm not a professional at this point. But my lighting is good. My thing is good. My webcam, I mean. Anyway. Looking back at this, we see this kind of triangle of zeros again. This 1, 1, 1, 1 in each column. This is actually called the echelon form. Now that's going to be discussed in 1.2 in the next chapter. But you should remember that echelon pretty much means staircase. And you could see from the 1, 1, 1 in each column that it is like a staircase. And your professor's probably going to cover that as well. Now, I have reached the two fundamental questions about linear systems. It's the last thing I wanted to discuss. The first is whether or not a system is consistent, which means that at least one solution exists. I should actually turn this over. You could see from here that a solution does exist. You have... what I'm going to do is actually I'm going to change this to the equation form. So that would be x sub 1 minus 2x sub 2 plus x sub 3 equals 0, 0 plus x sub 2 minus 4x sub 3 equals 4, 0, 0 plus x sub 3 equals 3. So here you could see that x sub 3 has a solution. You could plug this into x sub 3, so you could eventually find x sub 2. You could use x sub 3 and x sub 2 to plug into the first equation, so you could eventually find an x sub 1. So for that, I guess I'll do it over here. That would be x sub 2 minus 4x, I'm sorry, 4 times 3. equals 4, take x sub 2 equals 4 times plus 12, which equals 16. And you take x sub 1 minus 2 times 16 plus 3 equals 0. X sub 1, let's see, what's 16 again? 16 times 2, it's 12 to 3, minus 32 plus 3 equals 0. X sub 1, oop, I'm running out of space, minus 29 equals 0. So x sub 1 equals 29. So your x sub 1, x sub 2, x sub 3 is equal to 29. What did I say? What's x sub 2? X sub 2 is 16, and x sub 3 is equal to 3. That would be your solution. And only one solution, mind you. So I believe the solution is also unique. I'll get to that in a second. Uniqueness, well, it is a little bit of a mystery to me. I don't like the way that the book explains it. But around the end of 1.1, the book explains that in this matrix, over here, this matrix, since you could only get x2, no, since you only have one x3, and you could only get x2 by using the second equation, this, and you could only use x1 by using the first equation, that this is unique. Again, this leaves me kind of yearning for a greater explanation and more examples of uniqueness, but sadly the book does not touch on that. Now, that felt very long to me. I'm looking at time. It took 22 minutes to get this far. I hope it's kind of digestible. It should be, because it's just the first section of the book, and I believe that even if you were to only read the book by yourself without the professor there, you could probably get this pretty easily. But some of us actually don't find that we are able to hold ourselves accountable to that. And we need this outside driving force, which I don't like. I don't like that. Hopefully one day we could actually go and bring this to our inside, an internal locus of control. You might not be aware of that if you haven't taken a psychology course. But enough of that about that. I'm just rambling now. I know that this came off as teaching from the book, because that was my intention. Ha ha ha. In later videos, what I'm going to try to do is get away from that. I'm going to try to use the comment section as much as possible, so please give me feedback, and I'll see if I could just, I'm not sure, phrase this in my own terms a little bit better, and try to really figure out how to improve. And that's why I'm really grateful to you guys that do leave me a comment. The usual thing, you've been on YouTube before, you know the usual ending, subscribe, like, ring that bell button. Come on, people. This is the only time I'm going to say that. I've been on YouTube for a little while now, and I already find that annoying. Just really, crap. I should really cut that from the the video, but I might not. I might just leave it as such. I'm probably going to do very little editing. I might decide to, if anybody could help me out, as a video editing software that I could probably use with a Logitech webcam, that would be great. And yeah, this is the end for section 1.1. It turned out to be almost as long as a lecture, which I enjoy. Okay then. For now, bye.